Hello students, today under the topic matrices and determinants, which is chapter 3 of class 12, we are going to take up the subtopic inverse of matrix by elementary operations. So let us start with elementary transformation or operations of matrices. There are 6 operations or transformations on a matrix, 3 of which are due to the rows and 3 are due to columns, which are known as elementary operations or transformations. So let us see one by one. Number 1 is the interchange of any 2 rows or any 2 columns. That means we can interchange any 2 rows and any 2 columns. Symbolically, this interchange of say ith and jth row, it is denoted by Ri, and this sign we use for interchange. Ri is interchange with Rj, and interchange of ith and jth column is denoted by Ci is interchange with Cj. So for example, if for this matrix A, a 3 cross 3 matrix, we are applying the operation of R1 interchange with R2. Now what will happen? Row number 2 will now become row number 1 and row number 1 will become row number 2. So this is the first transformation that we can apply. Number 2 is the multiplication of the elements of any row or column by a non-zero number. We can multiply any row or any column by a non-zero number. Okay. So suppose we are multiplying the ith row with k, which is a non-zero number, then this operation can be written as Ri is now interchanged to k times Ri, right? And similarly for column, say we are multiplying the ith column with k, we will write Ci is interchanged to k times Ci. For example, say this is a matrix which we are having as first row 1 2 1 and minus 1 root 3 1 as the second row, and there are 3 columns. Okay, 1 minus 1, 2 root 3 and 1 1. Now say I am applying the operation C3, means third column is now interchanged to 1 by 7 times C3. So what we need to do is, there will be no impact on the first column, no impact on the second column, but the third column here will be multiplied with 1 by 7. So it is 1 by 7 times 1 and again 1 by 7 times 1. Okay, this is how this operation can be applied. For the third one, the addition to the elements of any row or column, the corresponding elements of any other row or column multiplied by any non-zero number. So actually this is the combination of these first two operations, that what we are going to apply is, say suppose I want to now change my ith row as ith row plus k times the jth row. Okay, so what we need to do is I have to multiply the jth row by k and then add it to Ri, right? And that will transform the complete row Ri into that. Similarly for column, the operation can be applied as Ci is changed to Ci plus k times Cj. For example, I am applying the operation for this 2 cross 2 matrix as R2, means the second row is to be written as R2 minus 2 times R1. So what will happen now? This is row 2. So each element of row 2, now row 2 is to be expressed as this, where second row will now be written as R2 minus 2 times R1. Okay, so first row is as it is, second one is 2 minus 2 times of 1 is 0, and minus 1 plus say minus 2 times R1. So it is minus 1 minus 2 times 2 will be your minus 1 minus 4, that is together gives you minus 5. Invertible matrices. If A is a square matrix of order M and there exists another square matrix B of same order M such that AB is equal to BA is equal to I, right? So if a square matrix of order M is there and another square matrix of same order is occurring, whose name is we are taking as B, right? So in general we know that matrix multiplication is not commutative. That means product AB is not equal to BA. But here if two such matrices are there such that AB is equal to BA and both the result are equal to I, then B is called the inverse of matrix A and is denoted by A inverse. A inverse. In that case, A is said to be invertible. For example, if A is a 2 cross 2 matrix we have taken here, this is the first row, this is the second one, and B is a matrix 2 minus 3 and minus 1 2. Both are 2 cross 2 matrices. So let us check out the product. The product here, it turns out to be I. I means the identity matrix. And similarly, B also turns out to be the identity matrix, right? So in that case, B is called the inverse of A, right? or in other words we write B is equal to A inverse. Now say if B is equal to A inverse, then definitely A is also inverse of B, right? So A is inverse of B, that means we can write A is equal to B inverse, that means both are inverse of each other. One important fact that we need to note down is that only square matrices, they possess inverse. Okay, rectangular matrix, they do not possess inverse. Why? Reason is that for product BA and AB to occur, right, to be defined, because the condition regarding the number of columns of first should be same as the number of rows of second matrix. If they are to be meet out, right, so we need to take both of them as your square matrices of same order, right? And moreover, the second condition is that if B is inverse of A, then A is also inverse of B. That means both are inverse of each other. Now let us check out theorem number 3, which is uniqueness of inverse. Now what does it mean? It means that inverse of a square matrix, if it exists, is unique. That means if the inverse of a square matrix is existing, then this inverse is unique. So how will we prove it? Let us start with the proof. So first of all, we need to consider a square matrix. So let A is equal to Aij, right? A is equal to Aij be a square matrix of order n. This is a square matrix of order n, right? And if possible, let B and C, suppose B and C, they are also two matrices, two another matrices, they are two inverses of A. Okay, two inverses of A. So what do we need to prove? We need to prove that since it is saying if the inverse is unique, that means B and C should be same. Even if we are supposing two different inverses of this matrix A, so we should come out with the conclusion that B is equal to C, right? So what we need to show, that we shall show that B is equal to C. Okay, now let us start. Since B is, it is given B and C are two inverses of A. So since B is inverse of A, matrix A, so by definition what do we get? We get AB is equal to BA is equal to I. That the product AB is equal to BA is equal to I. Again, since C is inverse of A. So what does it mean? It means that AC is equal to CA is equal to I. Means the product of both, it commutes also, commutative property holds, and result is equal to the identity matrix also. Now I need to prove B is equal to C. So let us see, I will start with B. Okay, and I will prove that this turns out to be C, equal to C. So how do we do it? By using these both equations. So can I write B as B into I? Yes, because a matrix multiplied to identity matrix is the matrix itself. So B can be written as B into I. Now I need to introduce C definitely in some or the other manner, right? So for C, I will use this equation, right? Because there is no C. So C will come out from here, right? It is from here, right? So the value of I from here I will change as AC. Okay, this I will change to AC. This will help me in taking out or getting out my C. Okay, because I need to introduce C. Now this is equal to, can I apply the associative law? Yes. So it can be written as BA into C. Okay, now BA by equation number 1. By equation number 1, here I used equation number 2, by which it turned out to be this, and now I will use equation number 1. So it turns out to be I into C. So this is by equation number 1. And what is I into C? It is equal to C. So what do we get? B is equal to C. So which clearly means that inverse of a square matrix, if it exists, is unique. Now, theorem number 4 is if A and B are invertible matrices of same order, then AB whole inverse is equal to B inverse A inverse. Same as we studied in transpose law, that AB whole transpose is equal to B transpose A transpose. So this is called as invertible law. This is called as invertible law. So how we are going to prove it? Now we know by the definition of inverse. Let us start with the proof. So by definition of inverse of matrix, can I say that AB product AB into its inverse, right? As we know that A into A inverse is I, or AB is equal to I, then B is inverse of A, right? We are familiar with this property. So a matrix into its inverse, this result turns out to be I, right? So a matrix AB, we are taking here the matrix as AB. So matrix AB into AB whole inverse, this is equal to I, right? Now what I need to do is I need to introduce this A inverse, right? So what will I do? I will pre-multiply by A inverse. So what will happen? Pre-multiply means in front I will write A inverse. AB, this is AB whole inverse. Situation is that I should just in this side will be having only this AB inverse, and this side I'll be getting B inverse, A inverse, right? So firstly I'm pre-multiplying by A inverse and then I'll pre-multiply by B inverse, okay? So this is how helping me. It is A inverse into I, A inverse into I. It is giving me A inverse into I. Okay, pre-multiplying by A inverse, both sides, right? Now I will work out for some association. So A inverse into A, this, right, into B, B is left alone, into AB whole inverse. Now this B will be balanced by that B inverse, okay? And a matrix multiply with your identity matrix will give you the same result as A inverse into I will be equal to A inverse, right? Now again, this A inverse into A or A into A inverse, that will give me result as I into B, okay? I into B, and that is AB whole inverse, and this is A inverse. Now I into B, again I into B is your B itself, so it is B AB whole inverse equal to A inverse. Now again I need to balance it, so what will I get? I need to pre-multiply by now B inverse, so it will be B inverse B and AB whole inverse. So pre-multiply means I should put it in front of this A inverse. So again this will be your I, again by this rule. So I into AB whole inverse is equal to B inverse A inverse. Why? Because a matrix multiplied to its inverse is identity matrix, and identity matrix multiplied to another matrix, AB whole inverse is another matrix. Now it is your AB whole inverse is equal to B inverse A inverse. This is what we mean to say by invertible law. Inverse of a matrix by using elementary operations or elementary transformations. Now let X, A and B, they are matrices of same order. Three matrices we are going to take, X, A and B, such that X is equal to the product of A and B. Now in order to apply a sequence of elementary row operations on the matrix X is equal to AB, this equation, we will apply these row operations simultaneously on X and on the first matrix A, okay, on X and on the first matrix A of this product AB on right hand side, right? Similarly, in order to apply a sequence of elementary column transformations or operations on the matrix equation X equal to AB, we will apply these operations simultaneously on this X and to the second matrix B, right? Second matrix B of this product AB, right? For row operations, we will apply our row operations on this X and this matrix A, whereas for product X is equal to AB and using elementary column transformations, we will apply our operations on this matrix X and on the second matrix B. Now, in view of this above discussion, we conclude that if A is a matrix such that A inverse exists, then to find this A inverse using elementary row operations, we need to write A as A is equal to IA. Okay, and then we apply a sequence of operations, sequence of row operations on this A is equal to AI till what time? Till the time here we get I to this side and we get a matrix, some matrix B to this side, and then A is already there, right? So on A is equal to IA, we apply operations till we get I is equal to BA, right? And the matrix B will be inverse of A. Similarly, if we wish to find A inverse using column operations, then we need to write this A as A is equal to AI and apply a sequence of column operations on this A is equal to AI till the time we get, instead of A, it changes to I, and this A will be as it is and this I changes to some B. Okay, so we will apply a sequence of column operations on A is equal to AI till the time we get it as I is equal to AB, right? In case one or more of elementary row or column operations are applied, okay, on this A is equal to IA in case of row operations and A is equal to AI on column operation, and it happens that we obtain all zeros in one or more rows of the matrix, right? That one or more row, it turns out to be completely zero. In that case, we say that A inverse does not exist. So let us take first question. Using elementary row transformations, find the inverse of the matrix if it exists. Okay, if the question is just using elementary transformations find the inverse, then you can go for either row or column with which you are quite comfortable. Okay, but if it is mentioned you have to use row transformations, you need to go for row transformations, or for column in the same way, right? So let us start with our solution. And how do we start? For elementary row transformations, we write A as I into A. A is equal to I into A, right? And then this is your 2, 2, 3, minus 3, 2, minus 2. This is 3, 3, 2. And I here is 1, 0, 0, 0, 1, 0, 0, 0, 1, and this is as A. Okay. Now I need to apply my row transformations, means I will apply transformations row wise, row 1, row 2, row 3, okay? Keeping in mind in such a way that this side reduces to I, and definitely the same operation will be applied this side, so some matrix will appear here instead of this identity matrix, right? And that will be called as your A inverse, and this A is as it is, okay? So the key factor to remember here is that it is suggested that while applying the row operations, proceed in such a manner that you fix column wise first. Okay, that means you first need to make this our entry, first entry as your, this entry as 1, then this is 0, and then this is 0. Then you will pick up this as 1, okay, then both of them 0, and then this one, and then both of them 0. Okay, in that way if you will proceed, means you will start settling down the columns while applying row transformations and rows while applying column transformations. It will be easier for you to get the correct answers. Okay, so first thing is I should make my mind that I have to firstly make it 1, 0, 0, then this as 1, then this as 0, 0, and then this as 1, and then both of them as 0, 0. Okay, so keep it in mind and let us start. So first of all, this is in row 1. Okay, think of the rows. So this element is present in row 1. To make it 1, I need to write it as half of R1. So half of R1 is your 1 minus 3 by 2. This is 3 by 2. The rest of the rows are same. Same thing is there, and this is A. Okay, now I need to make these two entry zeros using row 1. Okay, so the operations will be row 2, R2 minus 2 times R1, and R3 minus 3 times R1. So this will be your first row will be same as no operation is applied here. R1 is serving as the doctor and R2, R3 as the patients. So only operations surgeries will be applied to row number 2 and row number 3. We can remember it in this manner. Okay. And it is suggested don't apply in the same step operation on R1. Right. Treat it as that it is a serving doctor right now and he is treating the patient, so operation cannot be applied on it. Right. In the same step. In the very next step you can apply operation on R1. So this is R2. 2 minus 2 is 0. This is, you can work out it here, 2. Okay, minus 2 times minus 3 by 2. So this is your 2 plus 3, that is 5. Okay, and here 3 minus 2 times 3 by 2. So this is 3 minus 3, that is 0. Okay, and R3, 3 minus 3 is 0. This is R3 minus 3 times R1. So this is minus 2 plus 9 by 2. So this is minus 4 plus 9 by 2, that is 5 by 2. Okay. And again this one, 2 minus 3 times 3 by 2. So this is 4 minus 9 by 2. This is minus 5 by 2. Same operation I am applying here, R2. So R1 will be same, R2 minus 2 R1. So R2 minus 2 into half. So this is minus 1. So this is 1 and this is 0. R3 minus 3 R1. So R3 0 minus 3 times this is minus 3 by 2. This is 0 as it is and this is 1 as no element is there in row number 1 up here. Okay. Now the next step is to make this entry 1. In which row it is present? In row number 2. So row 2 will be written as 1 by 5 times row 2. So this is your 1 minus 3 by 2, 3 by 2. This is 0, 1, 0, 0, 5 by 2, minus 5 by 2. To this side, again the same thing. Row number 2 is minus 1 by 5. This is 1 by 5. This is 0. And the rest of the rows are same. Now using this one, which is in row number 2, okay, I will make these two entries 0. So the operations will now be using R2. R2 will be used to apply operation. R1 is R1 plus 3 by 2 times R2 and R3 as R3 minus 5 by 2 times R2. So let us apply these operations. So R1 is your 1 because plus 3 by 2 times R2 is 1 plus 3, 0 is 0. So minus 3 by 2 and this is 0 and this is 3 by 2 plus 3 by 2 times R2. This again is 3 by 2 as nothing is here. Okay. Second row is same as no entries there. And for R3 is R3 minus 5 by 2 times R2. So this is R3 minus 5 by 2 times. So this is 0. Okay. 5 by 2 minus this is your 0. And this here are R3 means minus 5 by 2 and this is your 0 into R2. So R2 is 0, so this is just minus 5 by 2. Okay, this is equal to your first row is half. So let us work it out somewhere that it is, we can work it out here that it is your R1, okay, plus 3 by 2 times R2. So this is half minus 3 by 10, which is your 5 minus 3, that is 2 by 10, that is 1 by 5. Okay. Second entry is this 0 plus 3 by 2 times R2. So this is your 3 by 10. Okay. And the third one is your 0 plus 3 by 2 times R2. So this is already 0. Okay. Now second row is same as no operation is required to be applied on this, and this is R3. So R3 is your minus 3 by 2, okay, minus 5 by 2 times my R2. R2 is minus 1 by 5. Okay, so this is your minus 3 by 2 plus 1 by 2. So minus 3 by 2 plus 1 by 2 is minus 2 by 2, that is minus 1. Okay, and second entry is your again R3. R3 here is 0 and this is minus 5 by 2 times R2. So this is your minus 1 by 2. Clearly we can see. And the last one is 1 because minus 5 by 2 times R2 will be giving just as 0. Okay. So now the next target is I have fixed column number 1, column number 2. Now the third column is to be fixed while applying row operations, remember it. So I need to make this entry as 1. So this is present in row number 3. So row number 3 is to be written as 2 by 5 times, minus 2 by 5 times to make it 1. Okay, R3. So it will be 1, 0, 3 by 2, 0, 1, 0, and this is 0, 0, and this becomes as, okay, this becomes as 1. So 1 by 5, rest of the rows are same. So minus 1 by 5, 1 by 5, 0, and this is your 2 by 5 as minus 2 by 5 is multiplied, right? So minus 2 by 5 into minus 1 by 2. It will be just your plus 1 by 5. Okay, so be careful while applying all these operations because this plus and minus sign affect the entries a lot. Okay, and the last one is your R3 is your minus 2 by 5. So it will be minus 2 by 5. Now everything is sorted. So by using this entry as 1 which is present in row 3, so I'll use R3 to apply operation on R1. Just one row is left on which the operation is to be applied. So operation will be 3 by 2 minus 3 by 2, 0. So R1 minus 3 by 2 times R3. So let us apply. It becomes 0. So identity matrix is sorted here. Now we need to be a little bit careful while we forgot to put A here. We need to put A alongside. Okay. So now this is your R1 minus 3 by 2 times R3. Just one operation is there. So I'll work it out somewhere. Okay. So this is R1, okay, minus 3 by 2 times my R3. R3 is 2 by 5. So this is your 1 by 5 minus 3 by 5. So this is minus 2 by 5. Okay. And then next is your 3 by 10 minus 3 by 2 times R3. R3 is 1 by 5. So this is again 3 by 10 minus 3 by 10. We can see that it comes out to be 0. And this is 0. Okay. Minus 3 by 2 times R3 is minus 2 by 5. So it turns out to be 3 by 5. And the rest of the rows are same. So this is 2 by 5, 1 by 5 and minus 2 by 5. And we changed this left hand side to I, and this is the matrix which we got here right now is the required A inverse. So next question is using elementary column transformations find the inverse of the matrix. So what do we do for column transformations? We write A as AI. Okay, so A is 1 minus 3 2 3 0 5 minus 2 minus 5 0. This is A and I is 1 0 0 0 1 0 0 0 1. So I need to apply such operations column wise now that this side changes to identity matrix and this side will change to some matrix which will be the required inverse. Okay. Now for row transformation we fix the columns first like 1 0 0, then this 1 0 0 and then this 1 0 0. But for column transformation we'll fix through the rows. So this is 1 0 0, then 1 0 0, then this 1 0 0, right? So see, as I have to proceed column wise, so this is column number 1 and number 2 and number 3 are to be treated, and as a bonus fact this is already 1. I need not fix this column as 1, so this is already as 1, so my 1 operation is reduced here. Okay, so this is C1 and these are C2, C3. So operation will be C2 as C2. So 3 minus 3 is 0. C2 is C2 minus 3 times C1. And C3 is C3. So minus 2 plus 2. So this is plus 2 times C1. Okay. So let us check these operations. So this is first column is same. So C2 minus 3 times C1 is 0. 0 minus 3 into minus 3 is 9. 5 minus 3 to the 6, that is minus 1. So C3 plus 2 times C1. So minus 2 plus 2 is 0. Minus 5 minus 3 to the 6 is minus 11. And 0 minus, this is plus. So plus 2 to the 4, that is 4. Okay. So C3 0 plus 2 times 2 is 4. So same thing I need to do here. So first column is your C2 minus 3 times C1. So this is minus 3, okay, and rest is same. And for C3, C3 plus 2 times C1. So this is same as it is, because you can see that only this entry will be C3 plus 2 times C1 and rest are 0. So we will get just it as 201. Okay, now next thing is to fix this. Okay, so this is in column number 2. So C2 is 1 by 9 times C2. So I just need to operate my column number 2 only. So this is 0, 1 minus 1 by 9. Rest of the things are same. Here also, this is 1, 0, 0. This is minus 3 upon 9 is minus 1 by 3. This is 1 by 9, 0, 2, 0, 1. Okay. Now with the help of column number 2, I'll make these 2 0. So operation will be C1 as C1 plus 3 times C2. So C2 is behaving as a doctor and C1 and C3 are patients. So your minus 3 plus 3 are 0. So this is your C1 is C1 plus 3 times C2. And the next operation is C3 and again plus 11 times your C2. So let us check out what is going to happen here. So first operation is on C1. So C1 plus 3 times C2. So this is 1 minus 3 plus 3 is 0. So 2 minus 3 by 9. Minus 3 by 9 means it is 2 minus 1 by 3. 3 by 9 is 1 by 3. So this is 3 to the 6 minus 1 by 3, that is 5 by 3. Okay, same thing here. It is 1. Okay, C1 plus 3 times this. So 1 plus 3 times minus 1 by 3. So this is 1 minus 1, that is 0. Again, your C1 plus 3 times C2. So this is 3 by 9, that is 1 by 3. And this is again 0, as nothing is there to be added. Okay, column number 2 is same as it is just used for operation. So this will be same. Now my next thing is our column number 3. So C3 plus 11 times C2, this C2. So 0 plus 11 times 0 is 0, minus 11 plus 1 is 0, and this is your 4, okay, plus 11 times minus 1 by 9. So this is 36 minus 11 by 9, that is 25 by 9. Here 2 plus 11 times minus 1 by 3. So this is 6 minus 11 by 3, that is minus 5 by 3. Again, this is 0 and this is plus 11 times this. So this is 11 by 9. Okay. And this is your 1. Okay. This is 1 plus 11 times this. So this is already as 1. Now I have fixed the 2 rows. Now I will fix the third row. So this is to be made as 1. So the operation will be C3, as it is in column number 3. C3 is 9 by 25 times C3. So no effect to anything else, any of the columns. So this is 1 by 9, this is 0, 0 and 1. So here also 0, 1 by 3, 0, minus 1 by 3, 1 by 9, 0. So this is your 9 by 5 times, 25 times. Okay, so minus 5 by 3 into 9 by 25. So this is minus 3 by 5. Okay, so this is again 11 by 9 into 9 by 25. So this is 11 by 25. And again it is your 1 into 9 by 25. So this is again already 9 by 25. So we have fixed up to here. Now the operation which will be applying, I will be now taking this to apply operation C3 and will apply operation on C1 and C2. So 5 by 3 will be made 0 by subtracting 5 by 3 times C3, and your C2 will be C2 plus 1 by 9 times C3. Okay, so let us apply. So C1, okay, 1 and 5 by 3 times C3 is 0. Again next is 0, no effect to this, and this will turn out to be 0. Again C2 plus 1 by 9 times C3. So this is 0. So this will be 1, no effect. So and the last minus 1 by 9 plus 1 by 9 is your 0. And I think we are done with our identity matrix to the left hand side. Now let us apply the same operation on right hand side, and we need out some calculation work. So C1 minus 5 by 3 times C3 is here. So this is your 0 minus 5 by 3 times minus 3 by 5. So I'm getting here as 1. Okay, so I'm getting here as 1. And then C1 minus 5 by 3 times this C3. So this is 1 by 3 minus 11 by 15. So this is 15. So this is minus 6 by 15. 3 to the 6. 3 5s are 15. So this is minus 2 by 5. Okay. So this is your minus 2 by 5. Okay. Now the next entry is 0. Here it is 0 and minus 5 by 3 times C3. So this is 3 3s are 9, 5 5s are 25. So this is your minus 3 by 25. Okay. Now let's fix the column number 2. Okay. Column number 3 will be same. So column number 2 is, say, minus 1 by 3. Okay. C2 times C2 plus 1 by 9 times C3. C3 is this. So this is 3 3s are 9. So minus 1 by 3 minus 1 by 15. So this is 15 minus 6 by 15. So that is again minus 2 by 5. Okay. Now next is your again C3. So this is 1 by 9. Okay. C2 1 by 9 plus 1 by 9 times C3. This is 11 by 25. Okay. So 11 by 25 here. So the LCM is 225. This is 2. Okay. And this is 25. Okay. And plus 11. So how much? It is 36 by 225. Okay. This is 9 4s are 36 and this is 9 2s are 18 and 9 5s are 25. So I'm getting here as 4 by 25. Okay. And the last one is 0 plus 1 by 9 times C3 here is 9 by 25. So this is 1 by 25. Okay. And the last column is as it is, as no treatment was done on this. So it is minus 3 by 5, 11 by 25 and 9 by 25. So I changed this to A into A inverse. So what is A inverse here? It is 1 minus 2 by 5 minus 3 by 5 minus 2 by 5 4 by 25 1 by 25 minus 3 by 5 11 by 25 and 9 by 25. Okay. So dear students, you need to follow few steps to do this question without any error. So if you will follow this process, this question will be done with no errors. I hope everything is clear to you. Thank you so much.